So Jeremy got his PhD earlier this year in May from University of Las Vegas, University of Nevada, Las Vegas, sorry. And he works mostly on protoplanetary disk, planet formation, N-body stuff, and he's going to tell us about, well, planet formation around binary stars. And one thing I want to highlight here as a encouragement for our students is that, so Jeremy got his PhD, as I said earlier this year, so he spent 4 years on his PhD, but by the time he graduated, he's got about 8 to 10 first author papers. So I just wanted to bring that up, not to give you any pressure, but to encourage our students to let you know what is possible within a PhD, okay? So with that, let's welcome Jeremy to give a Kolga. So Jeremy, please start whenever you're ready.
All right, great. Yes, like I said, I'm going to be talking about protoplanetary disk dynamics around binary star systems. So you can see kind of this cartoon here. We have our binary stars here orbiting each other's center of mass, and commonly we observe a disk of gas and dust around the binary. This is called a circumbinary disk. And so mostly I'm talking about like the dynamics that happen within the circumbinary disk. So just to start, before we go into two stars, we can review how one star forms. So when we, in the galaxy, we have these large clouds of gas and dust. These clouds will condense and form a star. And as the star rotates, the surrounding cloud that didn't collapse, the star rotates into, or spins down into a disk. So you have a disk of gas and dust around the star. Within the disk, we have these rocky materials, and these rocky materials will eventually agglomerate and form protoplanets. And then these protoplanets that are still embedded within the gas disk will accrete gas as they orbit and develop what we see, like all the observations, is these gaps in these protoplanetary disks. And once the disk disperses, or about 1 to 10 million years later, the gas in the disk will disperse, and you're left with the remnant rocky material, which looks like our solar system. And if you look at our sun, for example, eventually it will evolve to a white dwarf. If you have a larger star, it will evolve to a neutron star or a black hole. And so when we talk about binary star systems, when you form these stars and these clouds, sometimes they have really high density, and these stars will kind of perturb one another and become bound. And you can have binary or even triple star systems. So during, like I said, during my PhD, I did 13 first author, looking at various steps of this process. Today I'll just be talking about my work on these protoplanetary disks, although I've done a lot of work on white dwarf pollution, and then habitability of planets, and also I looked at fast radiating bursts. But again, the majority of my talk today will just be looking at the circumbinary disks. So how common are binary systems? So like I said before, most stars form in relatively dense regions within stellar clusters. You can see this movie in the top right by Matthew Bate. You start with this giant cloud, it will collapse, and you have your higher dense regions are the lighter colors, and eventually you'll see that stars begin to form within these high dense regions shown by the light dots. So you can see that these clouds can form an enormous amount of stars. And again, some of these stars will be bound to another star and form a binary star system, or even a higher order star system. And when we look at the average eccentricity of these binaries, they're on average about 0.3 to 0.4 or 0.5 eccentricity, but also they can be higher eccentricity. And we see some systems that have a high eccentricity as 0.08. And so just as a refresher, the eccentricity is how oval-shaped the orbit is. So you have 0 eccentricity, the orbits are perfectly circular. But we do see a lot of highly eccentric binaries, and this is important later for the disk evolution. And when you look at these binary systems, this is an image taken by Alma, you can actually see a disk around the binary. And so this is the right panel next to it is a model of this. So it's a little cleaner. You can see actually see a disk around the binary with the two stars. And what we see when we observe these binary star systems is that these circumbinary disks are commonly misaligned to the binary plane. And this is just due to the chaotic nature of gas accretion. So when these stars are forming, you have these gas accretion events coming in at all different angles. So again, these are simulations by Matthew Bate. These three bottom panels show the formation of a circumbinary disk. You can see it's misaligned. You actually get two disks in this case because there's two events of accretion that happen at different angles. So it's just chaotic, and you can form highly inclined circumbinary disks around these systems. Also, you can form disks around each individual star, shown by these top four panels, and these disks are also misaligned to the binary plane. And in some cases, if you have a triple system, you can form disks around all three stars. So when we look at observations of these circumbinary disks, I've just shown three cases for example. For cage 15D, this circumbinary disk is inclined by 15 degrees relative to the binary orbital plane. RS-43, you can see it's a nice image here. We see the large circumbinary disk in this long horizontal line is inclined by 60 degrees to the binary plane. So it's a very highly inclined system. And we also see disks around each individual star. So in this case, we have three disks in this system, and each of the three disks are misaligned to the binary plane. Lastly, we look at HG-800 BABB. This is a part of a quadruple star system. There's two binaries. And so around the B binary, we see a circumbinary disk that's actually polar to the binary plane. So it's actually inclined by 90 degrees. And so this is the only case right now of a polar gas disk. And when we look at the interior of the disk, we have this cavity that's produced by the binary, but the material from the circumbinary disk will flow through the binary cavity and accrete onto the stars. And this is just because the disk is viscous, so there's a viscous torque. But also there's a tidal torque because the binary, as it moves around, has a tidal torque and it wants to prevent material from entering the cavity. But with observed parameters of the binary, the circumbinary disk, this viscous torque kind of outweighs the tidal torque, and material can flow into the cavity. So these actually can see this. This is a binary system BHB 2007-11. You can actually see this is imaged observation of streams from the circumbinary disk falling onto the stars, and actually these streams are feeding these smaller disks around each of the stars. And like I said, these gas disks will have a lifetime of about 1 to 10 million years. After that, the gas is depleted, and you're just left with the remnant rocky material known as these kind of like asteroid belts, or debris disks. And kind of studying these debris disks can give clues on how planets are forming in such systems. And one example, we see these debris disks in binary systems. So we have this system called 99 Hercules, which is actually a polar debris disk. So it's a 90-degree inclined asteroid belt around the binary. And so I'll kind of talk more about this. I did a paper on this 2020. So are there planets around binaries? The short answer is yes. So we know about 50 to 70% of stars have at least one planet Earth size or larger, and nearly half of the Kepler observed planets are in a binary star system. So you can actually form two types of planets in a binary system. You can form S-type or P-type. So the S-type planets are planets that form around the individual component of the binaries. So you have circumprimary or circumsecondary planets. Well, you can form P-type planets, which are planets around both stars. So they're called circumbinary planets. And so we know about 20 or so planets that are circumbinary. And for example, we have Kepler-47, which is a binary system with 3 circumbinary planets. I'll play the movie here. And again, these planets in this case are almost exactly coplanar to the binary plane. That's just because of observational bias. It's easier to see these coplanar planets than inclined planets. And when we look at these planets around binaries, the formation pathways are still largely unknown. And so that's kind of what my work is studying these gas disks, kind of hinting on how planets form in such systems. And these next generation telescopes, such as James Webb and the 30 millimeter telescope, will surely fuel the discovery of planets within binaries. And so I just will note that if you're a fan of Star Wars, there's Luke on Tatooine that has two stars. And so again, we know about 20 or so of these Tatooine planets that exist. So when we look at this grounded binary, I just want to point out a couple vectors before we get started. So we have our binary in the red here. If it's eccentric, there's an eccentricity vector.
Sorry, the screen's
Yeah.
Stuck actually. Are you on the next slide already?
Yes, right.
We're still on the Tatooine slide here.
Okay, hold on.
Okay, now it's updated.
Okay, how about, can you see a disk now, a blue disk?
Yeah.
Okay. All right, yeah, so sorry, we have, so to talk about some vectors, we have the orbit of the binary and these red here, and if the binary is eccentric, there's an eccentricity vector pointing towards periastron. And then we have the angular momentum vector of the binary. In this case, it's just pointing straight up. And if you have a disk, the disk has an angular momentum vector given by the blue. And if it's misaligned, the misalignment is just the angle between the angular momentum vector of the binary and the disk. And that's how we determine if the disk is misaligned. And so when we observe a lot of these misaligned disks, they won't stay misaligned. They're not stable that way. So they tend to undergo alignment because the disk is viscous, it leads to viscous dissipation, and the disk will align to a stable configuration. There's two types of stable configurations. If your disk is highly inclined, the angular momentum vector of the disk will tend to align to the eccentricity vector, and we end up with a polar disk. So like I mentioned before, there's two examples of polar disk, and so this is a stable configuration. So it's it evolves 90 degrees to the binary plane. If your disk is lowly inclined, the angular momentum vector of the disk will align to the angular momentum vector of the binary, and you'll end up with a coplanar configuration. So these are the two stable configurations that you'll have with the disk. And so observations I've said before, like RS-43 has a disk that's inclined by 60 degrees. Over time, that disk will either go polar or coplanar based on the disk parameters and also based on the binary parameters. And so kind of my work during my PhD dealt with using in-body dynamics like Mercury. So you can just kind of set up an asteroid belt here and kind of look at the evolution of these particles. But to model these circumbinary disks, I use a smooth particle hydrodynamics code called Phantom. So this is kind of a snapshot. It's a 3D code. So in this case, I have three views: X, Y, X, Z, Y, Z. And you can see the stars are given, the binary stars are given by blue. And in this case, we see the disk is inclined by 60 degrees given by the middle panel. If it was coplanar, it would just be horizontal. And on top of this, I've done, I use analytical calculations such as cyclic resonance theory and disk linear theory. So now I'll kind of just go an overview of kind of the projects I've worked on during my PhD. So if you have any questions, you can feel free to interrupt me. So first we looked at the evolution of a lowly inclined disk around an eccentric binary. And so kind of the motivation of for this was the observation of KH15D. That disk, the binary is really eccentric, has an eccentricity of 0.08. And the disk is thought to be lowly inclined, about 10 to 15 degrees. And so what we find is that due to the, so for the simulation, we start with a disk of 15 degrees. Due to the eccentricity of the binary, the disk will actually increase its tilt as it evolves over time. So it actually increases it to 50 degrees because of the torque from the eccentric binary. And so actually, when you can see it, it decreases its tilt. So it undergoes these tilt oscillations as it aligns to coplanar. And this is just because of the eccentricity of the binary plays a big role in this mechanism. So when we look at, for example, the left panel here is the inclination of the disk over time. It starts at 15 degrees. It undergoes these large tilt oscillations driven by the eccentric binary. And eventually, this disk will align to 0, align coplanar. But you can see during that alignment, you undergo these large tilt oscillations, and if you look at the first oscillation, it goes from 15 degrees to nearly 50. So that's a huge change in the inclination. And so as this disk is aligned to coplanar and undergoing these tilt oscillations, it will play a big role in how planets are formed. Because if you're forming planets as this disk is tilted, you might form misaligned planets in the system. And we can actually take this, look at this first oscillation. We can calculate this I max, which is just the increase in tilt on the first oscillation, and compare that to analytical theory. So our theory here is given by this solid line, and our dots are the simulations for this I max term. And you can see our simulations match the analytical calculations, which is always nice. So next, earlier last year, I looked at this system 99 Hercules, which again has the only known polar debris disk. So it's a kind of like an asteroid belt inclined by 90 degrees in the binary plane. And so we wanted to explore how is that possible. And so the short answer is that if you start with a highly inclined disk, again, the eccentricity of this 99 Hercules system is about 0.766, so it's a very highly eccentric binary again. When you start with a highly inclined disk, this disk will align polar. So you can see in the middle panel, it starts at 60 degrees, but the inner parts go polar first, followed by the outer parts. And so you get a disk that's at 90 degrees. And then when you look at, if you just look at the top panel here, the inclination of the disk, just pay attention to the dash and the dotted one. So the dashed line is actually probing the disk in the inner regions, and the dotted line is probing the disk in the outer regions. So you can see the inner regions go polar quicker, followed by the outer parts of the disk. And so from this, we can actually estimate a polar alignment timescale close to about 70,000 years. And so that is it's a lot quicker than the lifetime, a lot shorter than the lifetime of the gas disk. So again, a lifetime of the gas disk is compared to be 1 to 10 million years, and this polar alignment timescale we're seeing on the order of 70,000 years. So what this means is that for 99 Hercules, the gas disk went polar very quickly, and then that kind of dragged the dust into a polar configuration. And then once the gas disperses, the debris that's in a polar configuration is stable in a polar configuration. If your debris is kind of misaligned and you have no gas holding the debris, your inner parts of your debris that are close to the binary will process faster than the debris further out. And you remember it's like a spherical distribution like the Oort cloud. But you need, for this mechanism to work, you need the gas to go polar first, carry the dust, the gas can disperse, and you're left with your remnant polar debris disk. And so this is kind of interesting. So this is kind of interesting too, because if we have a polar disk, that means you can probably form polar planets. And so there hasn't been any polar planets detected so far because they're very hard to detect, via transits. But for example, this system here, the debris disk in 99 Hercules is actually very narrow. And it's kind of another thing I'm working on is that since this debris is very narrow, there's this thing called the shepherding effect, which you can have two planets on either side of a debris disk, and actually shapes the debris disk into a narrow ring. And so possibly this could be happening in this system. And so that gives rise to maybe there's polar planets that are around 99 Hercules. And so this is kind of a sketch of what a polar planet orbit would look like. We have our reference, our plane, binary plane in gray, and then the polar planet plane in red. So you can see here it's very hard to see very transits, because I guess if you're looking edge on the planet, the polar planet plane, there's times where the planet won't cross either of the stars. So you won't have these non-recurring transits in this case. And so this is kind of what I'm working on with Minkai currently, is looking at how the dust actually follows the gas during a polar alignment. And so the top panel here is the gas in the disk, and then the bottom panel is the dust. You can see here the top, both of them will undergo polar alignments, so they undergo 90 degrees, and we get in the disk, in the dust disk, we get these two rings that occur in the system. And so we're kind of looking at if the stream instability can operate in these polar disks with the dust. So that's kind of the stuff we're working on currently. All right, so those projects kind of dealt with the global structure of the circumbinary disk, but also I'm interested in the flow of material through the cavity. And so I want to introduce this mechanism real quick called the Kozai-Lilov mechanism, and this was actually found in 1962 independently. So Kozai-Lilov found this independently, and so basically what it is, if you take, for example, if you have an asteroid that's orbiting around the sun, and you have Jupiter as the perturber, if your asteroid is highly inclined, there's some threshold, which is about 39 degrees. If it's above 39 degrees inclination, it can trigger the Kozai-Lilov instability, where then the eccentricity and inclination of the particle are exchanged to one another. So, for example, I'll show this as a disk, so it's kind of easier to see. So we have a binary system, and we have an inclined disk around one component of the binary. So in this case, it's inclined by 60 degrees. It's above the threshold for the Kozai-Lilov instability, and then this disk will undergo these oscillations where it becomes very eccentric. And as it increases eccentricity, it decreases its inclination, and vice versa. So you can see here on the right panel for the disk, this is the disk eccentricity as a function of time on the top, and the inclination on the bottom. And so you can trigger these Kozai-Lilov oscillations where the eccentricity increases. As the eccentricity increases, your inclination decreases. And so this is actually really important in forming planets around binaries, because as you become very eccentric, your disk produces shocks, and these shocks can promote gravitational instability and fragmentation, and you can form giant planets in this case, and through this mechanism. So what I was interested in, again, for this simulation, we're just looking at a circumprimary disk. So what I was interested in is looking at, in reality, you have a circumbinary disk, and you have material feeding these smaller disks. And so I wanted to look at that through these simulations. So in this case, it's a very simple simulation where we have a binary around with a coplanar circumbinary disk, and we have material that will flow through the cavity and form these disks around each individual component of the binary. So you can see here we have these constant streams of material that are feeding these smaller disks in the binary. And so I want to see what if the disk is inclined, because in observation we do see a lot of inclined disks. So how does the gas flow in these inclined disks happen? So again, we start with a circumbinary disk, and we have our binaries in red. We have an inclined disk, in this case it's 60 degrees, and you form material flows through the cavity, and you form these highly inclined circumstellar disks around each star, and you can see that they're actually really eccentric. So since they're highly inclined, because the circumbinary disk is already highly inclined, the gas flow is highly inclined, it forms these highly inclined disks, and they trigger. Oh, sorry?
The movie, I think, is lagging a bit. Can you try again? Try again?
Oh, sorry. How about now?
I think we're a few seconds behind audio. Yeah, it's a little stuck. Okay, I have the file. Can you see our screen here?
Yes, I can.
Yeah, so latest.
Okay.
Yeah, so let me
Okay. Yeah, so I apologize for this. Yeah, so like I said, you can see I was interested in the gas flow of the highly inclined disk. So this movie started at initially at 60 degrees, and you can see the gas flowing in. It forms these highly inclined circumstellar disks, and these circumstellar disks will undergo these Kozai-Lilov oscillations. But the caveat is that for this simulation, you have an increase in the number, or so you have you have an active flow of accretion from the Circumbinary disk onto the circumstellar disks, and actually were prolonged because of little oscillations. And I don't think, I think I moved the plot out of the view when I sent it, so I don't have the plot to show you. But these oscillations, these extra oscillations, are actually more long-lived in the system because of the continuous accretion of material onto the smaller disks. So yeah, you can go on to the next slide. There's that image. So you can see on the bottom panel we see that's the eccentricity, and the top panel is the inclination of the disks, of these smaller disks. And you can see that these oscillations are more long-lived because of the presence of accretion. And so again, each time you get these high eccentricity phases, you can produce these shocks in these disks because the disks are eccentric, and then that could form giant planets via gravitational instability. We can't really capture that in our simulations, but that's been the work that's been done previously. Okay, next slide. And this is a paper I'm currently working on. This is a polar circumbinary disk, and looking at the flow of material through the cavity in a polar disk. And so you can see we actually form these polar circumstellar disks. So you have your smaller disks that are also inclined by 90 degrees. And so what we see is that in these polar circumstellar disks, you can actually get caused by little oscillations that occur within these small disks that are in polar configuration, which has never been looked at before. And so this is the paper that hopefully I'll be finished by the end of the year. Okay, yeah, next slide, please. And so all those previous projects dealt with a binary disk, so 2 stars. But recently I've done work on GW Ori, which is actually a triple star system. And so if you click, please. Yeah. So GW Ori is a triple star system where you had a tight binary orbit around a tertiary companion, shown by the movie there. If you click again, there should be another side of the observation. So when we observed these observations of the system were taken earlier last year, and by ALMA, and you can see that we see that there's a disk around the 3 stars, and this is a circumtriple disk. So like before, we have our circumbinary disk, a disk of gas and dust around 2 stars. In this case, we have a disk of gas and dust around 3 stars. And what the alteration shows that you see there's these rings that are seen in the disk with a really prominent gap between the inner and middle ring. So the question is, how do you get these rings in this circumtriple disk? And I will note that this disk, so the outer 2 rings are inclined by about 38 degrees to the plane of the triple stars, and the inner ring is almost to coplanar. So that means the inner ring has actually undergone alignment to the triple star plane, while the outer rings are dragged behind. And so you kind of get this warp that's produced. So if you get to the next slide. So you can see the top panel there. It shows, again, the orientation of the 3 rings, as well as the warp that's produced in the system. So the question is, how do you produce that prominent gap between the inner and middle ring? There's a work last year by Krauss and all, who suggested that this gap is produced by the torque from the triple stars. So the torque is actually carrying the disk and forming this gap. But we've shown that with our simulations that that's not the case. So the triple system doesn't, the torque control system does not break the disk. And it can break the disk if you have a very highly, if you have a high viscosity, you can break the disk. But for actually, operationally motivated parameters of protoplanetary disks, we don't see that the torque is the cause of this disk breaking. So now then we kind of provide another scenario where there's actually a planet that's carving that gap. And so if you play the movie, this is our movie where we just started at 38 degrees around a triple system. We initially started with a pre-carved gap. I can explain if anyone wants to know why we did that later. But our planet initially begins at 38 degrees. Because it's inclined around the triple stars, it will process its inclination, and as it goes out of the plane of the disk, because it undergoes these tilt oscillations, that gap just propagates outward because nothing's holding the gap. But as the disk kind of oscillates back in the plane of the disk, it starts to carve a gap again, which you can see at the last part of the movie. You can see the planet carving the gap. And so what we've, on those two right panels, the top one is the observations of the CO map. And so you can see there's a dashed curved line that represents the warp in the disk. And so what I've done is that I've taken the simulation with the planet carving the gap, and I've copied and pasted that dotted curve and put it on my synthetic CO map, and found that it fits really well. And so we're quite confident that there could be a planet that's carving this gap in this system, and if it's actually true, it's the first planet on a circumtriple orbit that could be present. Go to the next slide, please. This is a paper I submitted a couple months ago. It's under review right now, but looking at the formation of the debris disk around Beta Pic. So this is kind of outside of what I've usually done. So Beta Pic is around one star, and we see this debris disk that's actually warped. So that upper panel is the image from the Hubble Space Telescope. It's kind of hard to see, but if you look on the kind of the middle, so the upper part and the lower part, in the inner regions, you see kind of this flare from the observations, and that's actually due to the debris disk being warped. And I was interested in looking at this warp structure. So a lot of work has been done on Beta Pic, this debris disk. And if you look, there's two planets that have been confirmed. Beta Pic B is one of the first planets that was detected, and Beta Pic B is actually inclined by about 3 to 4 degrees relative to the spin axis of the star. And this small inclination is thought to drive this warp in the debris disk, and so that's been looked at before. But recently, last year, there was a confirmed second planet in Beta Pic called Beta Pic C. It's an inner planet, and I was interested in kind of revisiting this and seeing if this inclusion of the inner planet will have any effect on the debris disk structure. So can you go to the next slide, please? So what I did for this paper is I did hydrogenational simulations with the two planets, and these two planets are eccentric. And what we see on the top panel is the surfaces in the gas disk, and the bottom panel is the inclination of the gas disk. And so what I wanted to see is that if the warp is present in the gas disk phase, because I wanted to answer if this warp is produced after the gas disk disperses or before. And so you can see that the surface density profile is flat, and the inclination profiles are flat. So that concludes that this warp that we see must have occurred after the gas disk dispersed. So in that case, I then run in-body simulations. I run two different models. So the red is our initial distribution of particles that I've used. And so I've run two different simulations, one just with including Beta Pic B, one planet, and another including the second planet, Beta Pic C. The black is just with one planet, so you can see in the left panel, that's the tilt profile, so you can see that there's a warp presence, and that kind of matches what people have found before. And when I include the second planet, which is the blue, it's pretty much identical. Except for the eccentricity plot on the right, when you have two planets, there's kind of a more highly eccentric tail to the distribution. But looking at the warp profile, it's quite similar. So that means that the warp in the debris disk is mainly driven by Beta Pic B, the outer planet. So you can go to the next slide. actually apply the Laplace-Lagrange secular resonance theory to this system. And so what this theory is that you can calculate the precession frequencies of particles in the potential of the system. So what we see on the left panel is those horizontal lines are the eigenfrequencies of the two planets, and the black line is the precession frequency of a particle. And so where the precession frequency of the particle crosses the eigenfrequency of the planet, that's the location of a secular resonance. And again, the secular resonance is just when these two precession frequencies are identical. And on the right panel, I can actually produce the width of these resonances. So the two planets are given by the red dots. And so this is kind of the eccentricity as a function of radius. And you see these two asymptotic features that are exterior to the planets, and those are the two secular resonances. So when you have particles that are inside those widths, they will be, they're unstable. They'll be perturbed outward. And so you can see the blue dots are our initial distribution of particles, and then the black is about 20 million years after t equals 0. So you can see that around these secular resonances, particles are cleared out. And they're cleared out at about 25 AU, which is that sets the inner edge of our belt. And when you look at observations from the Hubble Space Telescope, it shows that the inner edge of the beta Pic debris is about 25 AU. So I'm quite keen that these secular resonances are what's sculpting the inner edge in the beta Pic debris disk. Go to the next slide. Another paper I submitted a couple months ago was looking at accretion of material. So again, we're kind of looking at how material flowing through the cavity and how it's accreting onto the binary. And kind of what the motivation behind this is that in the system HD 800 BABB, I mentioned before, it has a polar gas disk. And there's been recent observations of, they've measured an H alpha flux on the primary star. And you can actually, you can take that H alpha flux and calculate a mass accretion rate. And we've done this, and it's quite low, but it's still okay. That just means that, in these polar gas disks, there's material that are flowing through the cavity. So if you start the movie, you can see these large streams that occur. On the left is a coplanar disk, and the right is a polar disk. And they're both face on. And you see for the coplanar disk, you get these eccentricity, this clump that is produced. And so we want to start the movie over real quick, sorry. Yeah, so for this yeah, thank you. Yeah, so for the left panel is a coplanar disk, and so you can see it. You get this clump that's produced, and that's been seen before, but you don't get a clump that's produced in the polar disk. And so to go to the next slide, when we look at the, if you play, click one more time. This left panel is just looking at the clump. So it's an asymptotic angle on the y-axis, and as a function of radius. And you see the clump that's moving. That just means it's orbiting around the disk. And so when we look at the accretion rates for these two cases, coplanar and polar disks, you can see for the coplanar disk, which is given in blue, the accretion rates oscillate. So that means that there's times where the accretion onto the primary star is greater than the accretion onto the secondary star, and vice versa. And so this kind of explains, there's been observations of eccentric binaries that show that the primary accretion is higher. And this was thought to not be true, because if you take, your secondary star is your less massive star, it has a wider orbit, and it orbits closer to the disk edge. And so it should have a higher accretion rate at all times. But for an eccentric binary, you get this clump that's produced in the circumbinary disk, and that leads to this alternating accretion rate that we see. But when we look at accretion rate onto the from a polar disk, which is given by red, it's always flat, so you don't get this alternating preferential accretion. We find that the accretion to the primary star is always higher than the accretion onto the secondary star. So this is this paper is under review right now. Next slide. Okay, so I'm almost finished. So recently I've been interested in looking at flybys. And so what a flyby is, if you look at the panel on the top left, we have a disk around the primary star, and you have a flyby that's, again, it's on an unbound orbit, so it's either parabolic or hyperbolic, and it will pass around the disk, and as it passes around, it will perturb the disk. And so we see a lot of examples of flyby candidates. And so, for example, if you look at AS205, which is the third one, the flyby candidate is given by the bottom right-hand corner. And this flyby candidate is actually grabbing material off of the primary disk and forming its disk around its own star. These are candidates because it's really unclear if these are actually unbound companions or if they're bound, but they're just very long, eccentric binaries. And so kind of the work I'm doing, I'm kind of looking at the disk dynamics can hopefully disentangle these two. Let's go to the next slide. So if you could just play a movie. So this is, we're looking at a primary disk here, and the flyby is on parabolic orbit. It will fly by, and it will produce these spirals in the disk. So if you want, you can go ahead and play that again if you want. Go back one. Yeah. So as a flyby crosses periastron, it will produce these spiral features in the disk. And the right panel is just kind of looking at the density of these spiral arms for different perturber masses. So the top one's a 5 Jupiter mass, and then the bottom panel goes up to 100 Jupiter mass. And you can see within each increasing, when you increase the flyby, the spiral arms become more prominent. So you can go to the next slide. You can play this. So this is the kind of the same movie here. But when we see these spiral arms, we can calculate the pattern speed, so how fast these spirals are moving. So the black curve is the angular velocity of the flyby, and then those other curves are the primary and secondary spirals with two different radii. So we picked 75 and 85 AU. We can see, we can model the pattern speed, and they start a little higher, a little faster than the angular velocity of the flyby. That's just because the disk is already is Keplerian. So I show these two horizontal lines at top are the Keplerian velocities at 75 and 85 respectively. And so the spirals tend to start close in speed to the perturber, which makes sense. Let's go to the next slide. And also we can measure the pitch angle of the spirals that are produced by a flyby. And so the pitch angle is you have your logarithmic spiral, you have some sort of unit circle, and you can create the tangent. If you calculate the tangent between those two lines, you get a pitch angle. And so the pitch angle changes depending on what radius you pick. So if you go to the next slide, I can calculate the pitch angle. And so before you play the movie, the left is a movie looking at the azimuthal angle on the left, and as a function of radius in the disk, and the color is the surface density. So if you play the movie, this kind of just shows these spirals that are produced radially. So you can see the movie will repeat. But you can see we get these spirals that are formed from the flyby, and you can, if you actually measure the slope of those spirals as a radius, you can get the pitch angle from the simulation. So on the right is the pitch angle for 75 and 85. And you can see the pitch angle starts low, it increases, and then it starts to decrease. And the reason why it decreases is because these spirals are not, they don't stay around for a long time because the perturbers are long gone. So you have nothing to actually keep the spirals from dissipating. So eventually they do dissipate, but you can see here we have kind of this peak in this pitch angle, and I'm not sure kind of what sets that peak yet, so I'm still trying to figure that out. We go to the next slide. Yeah, you'll play the movie here. So this is actually a flyby for a stellar mass flyby. So it's a more massive flyby. It produces kind of spirals for a little bit, but then they go away really quick. And you can see for those in the classroom, the cavity becomes very eccentric. And so this eccentric cavity persists for a long time, on the order of the simulation time, which is about 20,000 or 30,000 years. And so on the right, I kind of show the eccentricity evolution for 3 different simulations. So the top panel is a flyby of 5 Jupiter mass, or 10 Jupiter mass, sorry. The middle one is for 100 Jupiter mass, and then the bottom one is for 1 solar mass flyby. And you can see the more massive the flyby, the more eccentricity growth there is in the disk. Again, this is kind of work I'm still going. Go to the next slide. So I have like 2 more slides and I'm finished. So I wanted to again show you this one, AS205, because it's very interesting flyby candidates. Again, we see that there's material being pulled off of the primary disk and a disk forming around the flyby. So you go to the next slide. I was interested in this formation or this mechanism. So in this case, we're going to start the movie. The left panel shows the disk face on. The middle panel shows the disk edge on, and the right panel shows the flyby itself. So you play the movie; they should all play at once. You can see on the left panel. You can see the flyby coming in. It will raise the disk and form its own disk, and this perturber is actually inclined by 45 degrees, and it forms a disk around the flyby. And what's interesting is that, comparing the right and the middle panels, the disk around the flyby is 90 degrees with respect to the primary disk. And so that's something that I did not expect to happen, and so that's something I'm kind of working to try and figure out why is there a mutual inclination of 90 degrees when the flyby inclination is at 45 degrees. So it's quite interesting. In this case, you form a disk that's polar, so you form a disk that's polar with respect to the primary disk. And so again, this is another flyby project that I'm working on currently. But if I go to the next slide, it's just my summary, so I'll leave that up. I'm sorry for the technical difficulties, but it's kind of just an overview of what I've done during my PhD and what my current work is. So thank you for your time.